coefficient we get is two equations, equation 2 and equation 3. We rewrite this equation 3 by taking this minus 2 cm minus 1 to the right hand side. We get here minus, this plus become minus, and m plus 1 and cm plus 1. Now we get the value of cm plus 1 divided by m plus 1. We get here minus 2 m plus 1 cm plus minus 1. So now this is my m is from 1, 2, 3 to infinity. We call this one as recursion relation. I need this place, and before going to use that one, I just want to get a quick revision of that what we have done. We started from the differential equation, first order differential equation y dash plus 2xy equal to 0. We can find here the coefficient of y dash is a1 of x is equal to 1. And we know that this is not 0 at any value. We take a special case when x equal to 0, this is not equal to 0. So we say x equal to 0 is ordinary point, because we will discuss the solution about the ordinary point. That's why we need the other point is singular point where this a2 of x is equal to 0. We're not interested in that one. So here we write the equation, the power series in terms of the at the point x equal to 0. So here we are having the sigma n is from 0 to infinity cn x power n. Expanded form is c0 plus c1x plus c2x plus c3x and so on. I told you that we are having the first order differential equation. We can keep one arbitrary constant for that one. Second order differential equation we get two arbitrary constants. Third order differential we get three arbitrary constants. So we try to find the value of c1, c2, c3 in terms of c0. So we are substituting this y, and then we need here y dash, as I explained before you. When take the derivative, then when derivative of c0 is equal to 0, derivative x is 1, we get c1, then 2 c2x, 3 c3x squared and so on. And in general summation form, we can write here y dash is equal to n is from 1 to infinity, n cn x minus 1. This is power rule we are going to apply. Now substitute the value of y and y dash here in this equation. Now the important thing, always remember, I told you in physics when I was giving the first one, when the coefficient as an x or x square or x minus 1, so always multiply the summation with that one, and then we take go to the next step. So multiply here by x, I get here the first term, and the second term is 2nx n minus 1. This is change here, so become here n plus 1. Now here, as I explained you, we want to do two things. Number one, we want to make the summations equal, so we can take it out, and the power equal, that we can take it out. So to make the power equal, we say this n minus 1 is equal to m and n plus 1 is equal to m. So then we see what the changing things will happen when we make this change. Then we get the value of n is equal to m plus 1, because we take 1 to the other side. When n equal to 1 here, then m is equal to 0. When n goes to infinity, then here n minus 1 also goes to infinity, so m goes to infinity. So our summation changes here. We are having here n is from 1 to infinity, so it become here 0 to infinity. I change n by m plus 1, and here also n by m plus 1, and here n minus 1 by m. We come to second term, we are having n plus 1. We take n plus 1 is equal to m, and my n is n minus 1. I change my n here. So when more, we have to change the summation, and summation when n is equal to 0, then m is equal to 1. When n goes to infinity, m goes to infinity. 2 is outside, we are having 1 to infinity. This change to m minus 1. Now this is my equation I get. Now here I have equated the powers. This is the power x to power m, we can take common. But here the summations are not equal. Then I told you that summation is very easy to take equal. We take one term from here out, m equal to 0. When we take m equal to 0, we get here m equal to 0, we get here 1. We get here c1, x to power 0 is 1. Then next term will be from 1 to infinity. So if we have to take two terms out, then we take m equal to 0, m equal to 1, and then next term will be 2 to infinity. Here we only take one term, because we'll change it to 1 to infinity, get c1. But here we don't need it. Now our powers are equal, so we can just take the summation out, we take the powers out, x to power m out, and the summation out, and we are having here this inside. So we compare the coefficient. The coefficient of x to power 0 is equal to 0, c1 equal to 0. Compare the coefficient of c1 is equal to 0 here, the coefficient 0, so this is equal to 0. We rewrite this one, this is my recursion relation, and onward I'm going to discuss. So we are having this recursion relation, cm plus 1 is equal to minus 2 over cm plus, or m plus 1, cm minus 2, cm minus 1. M is from 1 to infinity, we try to find the value of c1, c2, c3 in terms of c0. So we take here m equal to 1. When I take m equal to 1, I get here c2 is equal to minus 2 upon 2 c0, and I get here minus c0. When I take here m equal to 2, I get here C3 is equal to minus 2 upon 3. I'm having here m plus 1. And we take m plus 1, then we are having here the value equal to 3. So we are having here the value equal to C3 and 3, and here is C1. What is the value of C1? In equation 2, C1 is equal to 0. So this is equal to 0. Now get here m equal to 3. I get here C4 minus 2 upon 4 C2 minus C2 is equal to minus C1. So we get here minus 1 to power 2, 1 upon 2 C1, C0. So we put the value of 2 upon 2 that become here, that is here 1, this 2 upon 2 become 1, and 2 upon 4 become 1 upon 2, that is minus, and this minus become minus 1 to power 2. M equal to 4, we get here C5, and C5 is equal to minus 2 upon 5, C3, because C3 is 0, so this value is equal to 0. I get here M equal to 5, I get here C6 is equal to minus 2 upon 6, C4, and this become here minus 1 upon 3, C4. What's the value of C4? Value of C4 is here minus whole square 1 upon 2 C0. Or I can write this equal to minus 1 upon minus 1 become here minus 1 to power 3, and get here 1 upon 3 into 2 C0. Or we can say here minus 1 upon 3 into over 3 factorial C0 and so on. So similar to this one, I can say this is also is equal to minus 1 upon 1 to power 2 factorial C0, because 2 is 2 factorial, 6 is 3 factorial. I can write here my m equal to 6. We have C7 equal to 0. And we can have here m equal to 8, 7. We get here C8 equal to minus 1 upon 4, minus 1 to power 4, or 4 factorial C0. As I'm having here 2 factorial, 3 factorial, I'll get here 4 factorial. So I have these values. Now I substitute these values in my series and I can write my solution. Now my series I'm having here about y equal to 0, and we can just write the form of this one. I can write this one as my y is equal to C0 plus C1x plus C2x square, C3x cube, C4x4, C5x5, x5, and plus C6 and so on, x6 and plus so on. Now we can see here my C1 is 0, is equal to 0, my C3 is equal to 0, my C5 is equal to 0. What's my left? I'm left with here y equal to C0 plus C2x square plus you are having here C3, C4, C4x4 plus C6 x6 plus C8 x8 and so on. Our terms are gone. So we substitute the value. So my y is equal to C0 minus x square minus plus minus 1 to power 2, and this will become positive, over x to power 4 over 2 factorial. And then we are having here plus here again minus x to power 6, because we are having 6, where minus 1 to power 3 become minus sign. This is C0. Here is also this is C0. Also here is C0. This C0 x to power 6 over 3 factorial plus C0 x to power 8 over 4 factorial and so on. So this is the result I will get, the value of y, and this is my solution. So here I am having here the solution of my differential equation. I can just take here C0 out. So I can write here my solution as y is equal to C0 out. I get here this equal to 1 minus x square plus x to power 4 over 2 factorial minus x to power 6 over 3 factorial, and then plus x to power 8 over 4 factorial, then minus plus so on. So this is my solution of the differential equation we have started. I have few more notes to explain this one. This is my actual solution. On my differential equation, I have one arbitrary constant C0. Now this series here, I can write in terms of function of x. So it's very interesting. I can just show you how we can rewrite our solution as a function of x, and some more comments on the solution also I will make. So I have already discussed in the beginning the Maclaurin series, and one of the Maclaurin series we discussed for e to the power x. What's my series for e to the power x? My e to the power x was equal to 1 plus x square by 2 factorial plus x3 by 3 factorial plus x4 by 4 factorial and plus so on. If I change this series to e to the power minus x, I'll get here e to the power minus x. Replacing x by minus x, we get minus x. Get here plus x squared by 2 factorial minus x cubed by 3 factorial plus x4 by 4 factorial and minus plus so on. I change by x squared, so get here e to the power minus x squared, but we'll get here 1 minus x squared plus x4 by 2 factorial minus x6 by 3 factorial plus x8 by 4 factorial and minus plus so on. If you look on that one, that's the result, and we combine this result with this one, we get here y is equal to C0 e to the power minus x squared. So that's my solution in terms of a function. Here we have the solution in terms of a series. This is my note 1. I gave here, I said I will just discuss a few more, and we're having note 2. Note 2 is a simple method for solving the differential equation, which was y dash plus 2xy equal to 0. It is my dy by dx, and we can write here is equal to minus 2xy, separate the variable, dy upon y is equal to minus 2x dx. Integrate both the sides, we get here ln of y is equal to minus x squared plus ln of c. So get here y is equal to c e to the power minus x squared. The same result. It's a very simple one, but here we want to see how we can apply our power series method.